Hello, everybody, and welcome to this postgraduate course entitled by Grid Connected PV Solar Systems. This is Osama Azzat Abdul Latif, the module leader for this postgraduate course for the coming 15 weeks. And it's a pleasure for me to be with you during this semester. Actually, I used to teach this course since maybe 6 years ago, starting from 2017, but unfortunately, this is the first time to start recording this course over the internet. Let's now start sharing my PowerPoint slides and start with our first lecture with the grid connected PV solar system. Most likely, if you are attending this course on campus, so you have already attended the lecture number 0, where we have demonstrated together the main outline of the course and the main perspective and all these stuff together. But now let's start mainly into the core of our course, and maybe the first chapter can be titled by what is inside a solar cell. The first chapter is not actually not somehow related to the remaining of the module. So in the remaining part of the module, we are considering a macroscopic view, or what we can say a system level view. However, only in this chapter we are considering the microscopic view of a solar cell to understand the physics as a semiconductor and the optical carrier generation inside the solar cell, considering mainly the conventional silicon-based solar cell, and also giving some sort of highlight on other technologies like the scanning electron microscope image you see now for a perovskite solar cell, organic Dyson size, polymer based, and all these stuff. So let's start together with this first lecture. Before going into a solar cells, we have to consider first the material level of a solar cell. And here we have to consider the classification of a material. Of course, different disciplines can already study materials from different perspectives. But herein I am going to describe this from an electrical point of view. So the experiment is very simple. Whenever you have any bar of any material, of any unknown material, you can just go to the library, go to the lab. So we can, for example, let's use a whiteboard for a while. So let's assume that we have okay, that's great. So let's assume that we have any bar of a material like this. This is an unknown material, and you want to investigate what is the nature of this material, again from an electrical perspective. So what you are going to do simply is you are going to use some sort of a DC battery, a variable DC supply, and then you will connect here an ammeter. And in parallel, you are going to connect a voltmeter, as you know from your basic electronic classes or circuits class. So you are going to vary this voltage and then record the voltage value using the voltmeter and the current value using the ammeter, and you will have some table like that. So we have a certain voltage and a certain current, and you can plot this graph. Most likely you will have some sort of a straight line to this graph, where the slope of this line, assuming that this is voltage and this is current, so the slope here is 1 over the resistance, 1 over R, and you know that R equals to rho times L over A. Of course, sorry for my very bad handwriting. So R, the resistance, equals to rho, which is the resistivity, L, which is the length of this material, over A, where A is the cross-sectional area. So you can calculate R rho from here, and sigma, which is the conductivity, equals to 1 over rho. So you can calculate sigma, which is the conductivity of this material. This is a very simple experiment. You can do it anywhere. I think you can make it in a very easy manner. So if you did an experiment like that, and you calculate sigma, for different materials, for different nature of materials, different types of materials, you will have, I'm just searching for this. Yeah, we will have a lot of sigma. So now let's start with the sigma or the conductivity. You will find actually 3 bands of sigmas. So you will find some materials with very, very high sigma in the order of 10 power 7, 10 power 8, 10 power 4, 10 power 5, 10 power 6, and so on. And also you will find other materials with a very extreme low sigma in terms of 10 power negative 10, negative 9, negative 13, negative 14, negative 17, and so on. And you will find a third range of materials where you have an intermediate sigma. It's not as high as those, and it's not as low as others. Based on that, we can consider 3 types of materials from an electrical perspective. I'm quite sure that you already know this, which is conducting material or conductors, insulators, or their electricals, and also semiconductors. There is another physical way of expressing these materials related to what we can call the energy band diagram. The energy band diagram is simply the gap between the most or the highest filled band gap, energy band, and the first empty energy gap. So in conductors, for example, the valency band and the conduction band are nearly overlapped. So electrons doesn't need to do effort to transfer from the valency band to the conduction band. That's why you have a lot of free electrons in this conduction or in this type of material. Alternatively, or the other extreme can be demonstrated in insulators or the electrical materials, where the gap between the valency band and the conduction band is very high. So whatever energy you are going to give to the valency electrons here, they will not be able to transfer to the conduction band, and they will not be able to be a free electron. That's why they are insulators. On the other hand, this intermediate case, which is semiconductors, when you have a gap, but it's a reachable gap. It's a gap, there is a gap, but in some conditions, under some external or internal, intrinsic or extrinsic conditions, you may be able to transfer some electrons from the valency band to the conduction band. That's why we call it semiconductor. I think this may be very helpful to see it together to understand the concepts of a valency, of a conduction band, as usual. We will have this for the case of a silicon material. Silicon, if you remember from your chemistry classes, silicon contains 14 electrons. These 14 electrons are arranged with 2 electrons in the first energy level. This first energy level is the most energy level close to the nucleus. Then you have 8 electrons in the second level. Then we call this as a valency level because this is the last partially filled level. So we have here 4 electrons in the valency level. And then other levels are empty levels. Okay, so this is the demonstration, or this is the arrangement of the atoms inside silicon. This is a model for an isolated silicon atom. I mean, we here assume that we have only 1 atom of silicon, but in reality, we have billions of atoms of silicons connected together. So once we add another silicon atom, this silicon atom already have or has its energy level. So as you can see, each 2 energy levels of the same energy will start to overlap together. As you can see here, we have 2 levels, each with 2 electrons. Here we have 2 levels, each of 8 electrons. Here we have 2 levels, each of 4 electrons, and so on. So this is another. Then we have our third electron with the same, till we reach this structure. So now we have a lot of energy level, a lot of energy atoms. Accordingly, we have a lot of energy levels or a band of levels. That's why we call this an energy band, as you can see. So this energy band is formed due to an overlapped energy levels of the same energy. So as you can see, this is arrangement of silicon. So I think we can somehow move till we reach the point. Yes, energy band. Okay, so here, this is somehow important. So these two levels are core levels. We call them a core level. Actually, we can answer this question from two perspectives. The first perspective is that these two energy levels are completely filled energy levels. So the capacity of this energy level is 2, and you already have 2. The capacity of this energy level is 8, and you already have 8. So these two levels are full occupied. On the other hand, these two levels are very close to the nucleus, so the attraction force is maximum. This is another perspective. So these are the core levels, or the core electrons, because they are in the core levels. Now we have this valency electrons. I think we already hear this term since our high school chemistry courses, because we usually call these electrons in the outermost energy level, or in the outermost partially filled energy level, we call them as a valency electron. These valency electron, as I just mentioned, this is a partially filled energy level. The overall capacity of this energy level is 8. However, we only have 4 out of 8, so it's 50% full, and we call this valency electrons. So let's go to the next. This is a valency level. We already have mentioned this point. And we call this a conduction level. The definition of a conduction level is the first empty energy level. We call it a conduction for a conceptual meaning, because we believe that as far as the electron is here, that means that the electron is still partially bounded to the nucleus. If you give this electron some extra energy to move from this energy level to be energy level, now the influence of the nucleus is minimum, and herein the electron become a partially free electron. And this is the concept of a conduction, because as you know, conductivity is directly proportional to free carriers or free electrons. So you will say that when the electron reaches this level, now it's a free carrier. Now we can consider a conductivity for this material, and we can calculate the free number of the number of free carriers for this electron. So in the same manner, or using the same concept, we can apply the same concept on the bands here, as you can see here. So we have the first band is a fully band. It's a core band. This is the first band, as you can see. Same applied for the second band. The second band still is a complete filled band, which is cool. But now, or here, this is the interesting portion of the material, because these two levels are fully filled and highly bounded. So you are not going to break the bond here. No way. The probability exists here. Your targeted electrons are here in the valency band. And your target is to move these valency band electrons to the conduction band, where electrons become partially free. So if you just make a zoom in this area, and you call this bottom band as a valency band, and this top band as a conduction band, so simply you will have this structure. So you have a valency band, conduction band, and in between you have what's called an energy gap. And your target is to give this electron some sort of energy to move from the valency band to the conduction band. And the restriction here is that this energy should be greater than or equal the gap between the conduction and the valency. So this is simply how you can understand in a maybe a shallow manner the basic concept of the energy band theory in materials and especially in semiconductors. But let's go now to, we have a valency band and we have a conduction band. The question is, does the top of the valency band is typically aligned to the bottom of the conduction band? Actually, the answer may be yes or maybe no. In some materials, we have this structure. We have an top of a valency band, which is directly aligned to the bottom of a conduction band. And we call these materials as a direct band gap semiconductor materials. On the other hand, or let's see here, so we have here a very two important relations. So let me use again my whiteboard for a while, if you permit me. So let's assume that here we have a conduction band, and here we have a valency band, and let me use another. So here we have an electron. Okay, so there is two interesting phenomena can be studied here. The first phenomena, or what we can simply call absorption phenomena, when you have an external source of energy, E, and this E, this energy is greater than or equal the gap, the energy gap here. So electron can capture this energy. Of course, this energy may be a light photon, maybe a thermal energy, maybe any external source of energy, extrinsic or intrinsic. So whatever the energy is, this is not the point now. So we have an energy source, and this energy is captured by the electron. And as far as this energy is greater than the gap, so the electron will jump to this state and now leaving a hole in the valency band and create an electron in the conduction band. This is the first possibility. On the other hand, there is another interesting possibility, which is somehow far from our coast, which is when you have an electron here, and for some reason or another, this electron lose energy and go down to the valency band. So this loss of energy will be converted into the form of either what's called photons, which is the quanta of light. Again, I am sorry for this very bad handwriting. Or it can be phonons, which is the quanta of thermal energy. This actually depends a lot, based on a lot of factors. Again, this is somehow beyond the course interest. Maybe we will be more interested to the case where we have absorption of light, because this is typically the process of a solar cell, but maybe the other processes are related to other applications. For example, lasers are based on the stimulated emission of photons, where we have a light beams, or where we have a coherent light, which is a laser. But this is basically the main two probabilities that can occur between two energy levels, or between typically the valency band and the conduction band. Back to the presentation slides. And here we have our laser point. Okay, so we understand here, this is the energy gap. So you can absorb a photon. If you absorb a photon, then this light will move from the valency band to the conduction band, or these electrons will move from the valency band to the conduction band to absorb the photons, and the other possibility, as you can see. So this is the case where we have a direct band gap semiconductor material. In this case, as you can see, there is a change in energy. However, there is no change in the x-axis. The x-axis is what we call the k-axis, and this k-axis is somehow proportional to the momentum. If the momentum P equal h bar times k, where h bar is Planck's constant. Again, this is somehow a more physical perspective, which is a little bit far from the direction of this course on the system level, but this is just for your information. So we have this direct band gap materials, and we have the other case where we have an indirect band gap material. In the indirect band gap material, you have variation in both, as you can see, in the y-axis representing energy and in the x-axis representing momentum. But what is important here? What is really important here is the important point here, or maybe what is critical for us as a solar cells designer, is not somehow related to the direct or the indirect band gap. Of course, this is make difference, and you can easily understand this when you compare the performance of a silicon solar cells with respect to gallium arsenide solar cell. I believe that most of you already have read some sort of literature in solar cells, and you can easily compare the relatively low efficiency of silicon solar cell with respect to gallium arsenide solar cell. And one of the reasons beyond this is related to the NEK diagram arrangement, as silicon is a indirect band gap material, while gallium arsenide is a direct band gap material. But there is another important, or let me say, there is another more principal point here related to the limitation in the absorption. If you consider either band gap or direct band gap or indirect band gap, there is a limitation here that the absorbed photon energy should be greater than or equal the band gap. This is a very important theoretical limit related to any solar cell ever, that you will not be able to absorb all the photons across all the lenses in the spectrum. You have a very theoretical and sharp limitation here. You can only absorb photons which has energy greater than or equal the energy of a band gap. So let's reflect this on silicon, for example. This is a very important graph for us. We call this as the solar spectrum. In the y-axis, there is a parameter, or an arbitrary parameter representing the intensity, or we can say in between quotations, the number of photons. But what is more important for us is this x-axis representing wavelengths. And here you have place to avoid confusion, because energy and wavelengths are inversely proportional. The relation is a reciprocal relation. So as you know, energy equal h times mu, where mu is the frequency, and this mu equals c over lambda. So energy equal h c over lambda. So when I say that energy is high, a high energy will be captured here on the spectrum on a low wavelength. So the lower the wavelength, the higher the energy. That's why we call these ultraviolet photons as a high energy photons, while relatively the infrared photons, we call it a low energy photons. So now you can use this graph to know what we can call the theoretical limit of any solar cell. For example, let's consider silicon solar cells. Silicon has a band gap of 1.11, 1.12 in this range. The most famous number is actually not 1.11, which is written here in the slide. It's 1.12. This is more famous. In some texts, they just approximated as 1.2, but 1.12 is the most accurate, I think. So, as far as silicon has a band gap of 1.11 or 1.12, that means that energy or photons with energy greater than 1.11 electron volt only will be absorbed. So you can transfer this into the wavelength axis. You can see this limit, this vertical limit. So you will only be able to, let me use another color. Okay, perfect. So you will only be able to absorb this portion of the spectrum in the left-hand side. Let's use again the laser pointer. So this portion is the only available absorbed portion. Silicon are not capable of absorbing high or relatively high infrared photons. This is the first limit. But also, please take care that you also have another limitation here, another horizontal limitation. These horizontal limitations comes from the fact that if, for example, the energy of the band gap in silicon is 1.12 electron volt, and I give you, or I give a photon, I inject the material with a photon with an energy, for example, 1.5 electron volts. What will happen? Let's see. The first, you will input, the electron will, the first step is that this electron will capture the 1.5 electron volt. But it will find that it only needs 1.12 electron volt to jump from this state to this state. What should be done with the remaining energy? Simply speaking, this remaining energy will be transferred into kinetic energy in a form of a motion, which will result some sort of thermal energy due to collisions. So extra absorbed energy here will be transmitted into a thermal energy. And this is one of the main reasons beyond why solar cells become heated under operation. Maybe later on, when we consider our next chapter, considering a solar cell module on a module level, we are going to consider what's called the normal operating cell temperature, or the NOCT, which usually from 10 to 20 degrees higher than the working temperature. So, for example, we are now in the beginning of the autumn. The temperature is about 30, maybe in my office now the temperature is about 33. So if you have a solar cell fixed on my window here, then you will find its temperature from 43 to 53 degrees Celsius, which is the normal operating solar temperature for a solar cell. And this is the physical interpretation beyond why we have such an increase in temperature of a solar cell. So based on that, we can define what's called the theoretical limit, not only for silicon solar cells, but generally for any solar cell. A theoretical limit is the theoretical maximum efficiency that can be reached by a solar cell based on the active material used in the solar cell. Of course, one of the main challenges in the literature is, first, to reach an experimentally measured efficiency as close as to the theoretical limit. So, for example, in silicon, the theoretical limit is around 31%. By the way, this 31% has been proven maybe 60 years ago, typically in 1961, by a paper led by Shockley. Shockley is the very famous scientist who invented the transistor, and he got Nobel Prize on that. He published in 1961 a publication related to the theoretical limit of a silicon. I will give you an access to this publication on our e-learning page if you'd like to have a look on it. I think you can have a free version because this is part of the Science Direct Library, which is free using the Egyptian Knowledge Bank, EKP website for Egyptian accounts or Egyptian universities. So you can have a look on that. And this 31 is the maximum theoretical limit for a silicon solar cell. Practically speaking, there is some reported data about 25%, 26% for silicon, which is, of course, very, very good or very close to the theoretical limit. On the other hand, there is a lot of tricks how to bypass the theoretical limit by adding extra material, by adding extra structures, by a lot of mechanisms. Maybe we are not going to go deeply on that. Maybe I will going to show you some small examples on that, but it's more toward optical photon management, material science, semiconductor electronics, which is again somehow far from the perspective of this module, considering more towards system level analysis. Okay, so this is a very famous chart showing the progress of the efficiencies for different solar cells, and maybe it's now the time to classify solar cells. It's very, very, very debatable how we can classify solar cells. Maybe for myself, I now have 13 years of experience in solar cells, and I believe that I read more than thousands of papers in solar cells. And in each and every new review paper, you can see a new way to classify solar cells. But by a way or another, it will end up to the same approaches somehow. So some people classify solar cells based on generations. We call that we have a first generation, second generation, third generation, fourth generation, and so on. Other people are considering based on technology. So we have the conventional silicon technology, then the thin film technologies, then the organic and the electrochemicals, and we have the flexible and so on. So by a way or another, by the end of the day, you can have different approaches. These are one of the most updated classifications of solar cells. As you can see here, we have organic, inorganic, and hybrid. Again, this is one of the ways you can classify solar cells. But for me, maybe this is more toward, I would say this is more toward a material classification or a chemical perspective, electrochemical perspective classification. From an electrical perspective classification, I think the technology is the main aspect. So we start with a very conventional silicon-based solar cell, which is the most famous and most popular type of solar cell so far. Then we scale up to what's called the thin film technology. And then we go to a lot of new trends, including organic solar cells, polymer-based or flexible solar cells, Dyson-sized solar cells, perovskite solar cells, where most of the researchers see that, I'm one of them, see that perovskite solar cells is one of the most booming technologies in solar cells nowadays. So these are different types or different classifications, as I mentioned. By the end of the day, it's not important to restrict by one of these classifications, but it's important to have the microscopic view on different technologies, different materials, and different architectures and topologies. And let's go first to the most famous solar cells, which is the silicon-based solar cell. Whenever you are considering conventional silicon solar cells, let's say that we have 3 types of silicon as a raw material you can see in literature. The first is the most pure version, which is a crystalline silicon, crystalline silicon, leading to a crystalline silicon solar cell. The second is a polycrystalline material, and the third is an amorphous material. Maybe you can go into literature to know more about the atomistic arrangement in crystalline solar cells. We are considering a 3D atomistic periodic arrangement, an ideal arrangement. In the polycrystalline solar cells, we have some sort of a discontinuity in the arrangement, and in the amorphous, we have a random arrangement of atoms. It's now, yeah, it's more toward the material point. Maybe it is off topic. We can consider it as an off topic for some discussion in some lectures or so on. But these are the most famous structures. But how a solar cell, or let's go to the headline of this chapter. What is inside a solar cell? What is the basic principle beyond the solar cell? In order to understand the basic principles beyond, in terms of a solar cell, we have to understand what is called doping. So let's go to them. So what is a doping? So generally speaking, we have a silicon atom or any semiconductor, because mostly semiconductors are with 4 electrons in the outermost energy level. So let's assume we have silicon. So this is a silicon atom arrangement. As you can see, this is the atom or the core of the atom, nucleus and the core electrons. And around each silicon atom, we have 4 electrons, as you can see. And these 4 electrons are in a covalent bond with another 4 electrons, each from each one of its neighbors. So the silicon atom has 4 direct neighbors. So it has a covalent bond. I think you already know this information from your chemistry classes. On the other hand, as we mentioned earlier in this lecture, that you can also consider this silicon atom arrangement from a physical perspective as an energy band diagram. So in the energy band diagram, we have valency band, we have a conduction band, we have a band gap or an energy band gap, which is around 1.12 electron volt, as we mentioned. And we have what's called the Fermi level. Maybe I will not go deeply about the basics of this Fermi level. If you are interested to know more about the Fermi level, you can visit my lectures under the title of Solid State Electronics, ECE02C, where you can find a deep understanding of the Fermi level, either mathematically or physically. But to give a very quick illustration about what is Fermi level, you can easily understand that the Fermi level is the indicator of the electrons and the holes in the valency band and the conduction band. So what is the indicator, or how we can consider an indicator for an electrons and hole in the valency band and conduction band? Let's make it, or let's use the whiteboard somehow. Okay, so let's say that we have, this is a conduction band and this is a valency band. So this is CP. And this is the valency. Principally, at 0 degrees Celsius, you have electrons, or 0 degree, sorry, absolute 0 Kelvin. You have, let me use some circle. So you have electrons here in, you have some electrons here in the valency band. These electrons so far are a bounded electron. If you remember the energy band theory, these electrons are bounded electrons. So now, once we are working under the normal operating temperature, which is, for example, 273 Kelvin, this will produce some sort of, let me say, intrinsic temperature effect. So here we have some sort of a temperature. This is due to the 273 Kelvin. Accordingly, this 3/2 kT energy related to the intrinsic temperature effect will lead some electrons to jump from the valency band to the conduction band. And this will make, here we have electrons. And here in the valency band, we have what we call an empty gap, or typically in electronics, what we call a broken bond. So you have electrons now jump from the valency band to the conduction band and leave a broken covalent bond in the valency band. The broken covalent bond in electronics, we call it hole. So typically, due to this intrinsic condition, you have now 1, 2, 3, 4, 5 electrons in the conduction band. Again, if you remember from the band theory, whenever the electron is in the conduction band, we call it a free electron. And you have 1, 2, 3, 4, 5 holes in the valency band. So
number of free electrons in the conduction band equals to number of holes in the valency band. So, simply speaking, you can say in this manner that the Fermi level, which is an indicator, back to the slides. Okay, so the Fermi level, which is an indicator for the ratio of the electron in the conduction band to the holes in the valency band, will be typically in the middle of the energy band gap. This is because, as I just mentioned, for each electron moving from the valency band to the conduction band, a hole or a broken bond is created in the valency band. So number of electrons in the conduction band equals to the number of holes in the valency band. And that's the Fermi level is typically in the middle. And by the way, we call this, as you can see the title of this slide, intrinsic material or intrinsic semiconductor. Because if you just remember my whiteboard slide, the source where electrons move from the valency band to the conduction band is an intrinsic temperature source. I didn't do any extrinsic or any external effect to push electrons to move from the valency band to the conduction band. It is just the effect of the intrinsic temperature. That's why we call this an intrinsic semiconductor. Okay, on the other hand, can I do some external effects on a material? Of course, yes. We have what's called an extrinsic semiconductor. The most famous extrinsic behavior is the doping behavior. What is a doping? Simply, the doping is to add new material, we call it impurity material, to the silicon arrangement. So, by some extremely high force, I'm going to remove this atom, which is a silicon atom, and I'm going to replace it by another atom with another material, not silicon. We call it atom dislocation. We dislocate the atom and we put another atom in instead. Of course, it will not be one atom, it will be billions of atoms, but we are just describing this on a small scale. So, what is the new material you are going to add? What is the nature of the new impurity material you are going to add? Herein we have two cases. The first case is to add a fifth group material. When I mention fifth group material, that means that the number of electrons of this new material is 5 electrons in the outermost energy level. So, in the old scenario, this silicon atom has 4 electrons, which, as we said, have a covalent bond with 4 neighbors. Now, the new material, this one in blue, has 5 atoms. Accordingly, 4 of these 5 electrons, sorry, 5 electrons, not, I'm sorry, 5 electrons. So, 4 of these 5 electrons will have a covalent bond with 4 neighbors. And you still have 1 electron which has no available bond. Please remember, bond is an attraction force. So this electron has no bond, has no attraction force. So it can easily jump to the conduction band. But the question is, if this electron jumps to the conduction band, does a hole will be created in the valency band? Please remember, a hole is a broken bond. In this case, we don't have a bond. So when this red electron jumps to the valency band, no broken bond exists. Accordingly, you increase the number of electrons without increasing the number of holes. And that means your material now is turned to be what we can call an N-type material. Why it's an N-type material? Because in this case, the number of electrons in the conduction band is greater than the number of holes in the valency band. Based on that, if you remember Fermi level is an indicator. So your Fermi level will be no longer in the middle of the energy gap. It will move to be more toward the conduction band to indicate that the number of electrons is greater than the number of holes. So we have an shifted to up Fermi level with respect to the intrinsic case. Alternatively, you can do a similar process. If you add a material with a third group material instead of your silicon atom, again with a doping, but this time with a third group material. So your new material, this new green atom, will have 3 electrons in the outermost energy level with a covalent bond, but still one missing covalent bond exists. One broken bond exists. This broken bond, if you remember, my dear students, is a hole. So you create a hole without creating or without corresponding electron. Accordingly, you increase the number of electrons without increasing, you increase the number of holes without increasing the number of electrons, and then your Fermi level will be shifted downwards in order to have a p-type material, or in other words, a material where the number of holes in the valency band is greater than the number of electrons in the conduction band. So this is simply how you can construct an n-type material, how you can construct a p-type material, and in the next step, we are going to discuss together what if we combine an n-type material with an p-type material in one junction, which is called a p-n junction. Okay, so let's stop for this. In the next video, we are going to continue chapter 1 under the title, What is Inside a Solar Cell? Thank you very much.